We had 3 questions for homework last night. One of them was from worksheet number 7, question number 3. The other 2 were from page 534 in your textbook. I'm going to go over question number 1 and 2 from our textbook here in preparation for our quiz tomorrow that's on the exact same material. I told you there's no real tricks to tomorrow's quiz, but one thing that I will suggest that you pay attention to, and I honestly can't remember if this appears or not, but be prepared for things like unit conversions, centimeters, micro, coulombs, things like that, right? Those aren't real tricks, just things you got to always remember to do. All right, question number 1 says a small metal sphere X with a negative charge is directed to the left of another one Y. So this is going to be X, this is going to be Y. X has a charge of negative 2.5 coulombs. Y has a charge of plus 3.0 coulombs. And they are 0.012 meters apart. Sphere Z is directly below sphere Y. So let's draw that down here. Sphere Z is 0.012 again, directly below it. It has a charge of plus 4 coulombs. We want to find the net electrostatic force on sphere Y. Remember what we said yesterday? We don't expect to see a question where we want to find the force on X or Z here, because we're dealing with a funny angle then, right? But if we do, it's not a big deal. It's not a huge deal. It's just more work. If you do get a question where you have to find the force on X or Z, just take away the funny angle, get into X's and Y's, add up the X's and Y's, and then turn it into a triangle, a right angle triangle like we're going to do here. I'm almost certain that if we get a question like this on an exam, and there's a decent chance we will, it'll be like this, where you're trying to find the force on the one in the middle here. All right, well, what do? Draw a free body diagram here. We have a force of X on Y this way. It's to the left because Y is pulled towards or attracted towards X. What about the force of Z on Y? Well, that's a repulsive force because we have 2 like charges, positive and positive repel. Y is going to be pushed up and away, up and away. We're going to call that FZY. And then we calculate the values of both of those forces. Fxy is KQ1, Q2 over R squared. We're going to drop the sign of the charge there. Anybody have a value for that? For the value of Fxy? 4.68 times 10 to the 14 newtons. That's a pretty big force, eh? Why do you think we have such a big force here? Yeah, they're close together, yeah. Yeah, the bigger thing here is, well, I shouldn't say the bigger thing. They're both important here. But we're dealing with really big charges here, right? Usually we got charges that are smaller than that. We said it takes about 10 to the 19 electrons to make a coulomb of charge. And here we got 2, 3, 4 coulombs. So it's going to be a big force. And yeah, we're dealing with a small distance too. So both of those matter. All right, let's find Fzy. It's KQ1, Q2, Q3 over R squared. Distance is the same. What's the value of Fzy? It's going to be slightly bigger. Okay, same thing, just a slightly different number for charge Z as opposed to charge X. All right, now we're going to redraw this. We got Fxy that's to the left. We've got, has a value of 4.68 times 10 to the 14. We've got a value of Fzy, which is upwards, gives us a value of 7.49 times 10 to the 14. And our resultant force, which is what we're trying to find here, is the hypotenuse then. Do you see how, like, there's a few things you got to do here, right? But do you see how really the most important thing is this? Getting those directions right. You have no hope of getting the angle correct here if you don't get those directions. If you don't get those directions right. Okay, R is the square root of 7.49 plus 4 squared plus 4.68 squared. we should get a value of 8.83 times 10 to the 14. Pythagorean theorem. And theta will be the inverse tan function of 7 over 4, which gives us, I believe, 58 degrees. Is that right? 58 degrees. Had you drawn it the other way, you would have gotten 32 degrees. Yep. Yep. All right, let's take a look at question number 2 now, which is really the same question, except that we've got unit conversions to do here, right? We got centimeters, which of course we want to draw attention to, and we've got microcoulombs that we need to draw attention to as well. All right, so what do we got here? We want to find the force, the direction of the forces on B, is it? Yeah, on B, due to A and C. So what, A and B are opposites, so they're going to do what? Attract or repel? Yeah, they're going to attract. So that means B is going to be pulled towards A. Let's call that FBA, or my FBA force. Then we got a force of C on B. Okay, they're opposite charges as well. That's going to be a force of attraction. FCA is going to be downwards. C is going to pull B, sorry, C is going to pull, should be AB, right? Not BA. Force of A on B and the force of C on B. Does that make sense? You know what? It doesn't really matter what you call it. Okay, I like to use a consistent notation so that we can keep it straight. But if you called it FAB, it really wouldn't be the end of the world. It's not going to cause you to get the answer wrong. At least not most likely it wouldn't. All right, so let's get the value of FAB, my fab force. We got KQAQB over R squared. We got 8.99 times 10 to the 9 times QA is 2 times 10 to the minus 6. If you don't know what a microcoulomb is, or a nanocoulomb, or a micro anything else, then check your data sheet. In the middle of the back side of your data sheet, it has all of those prefixes. It tells you a micro is 10 to the minus 6. And all we got to do there is replace the micro, the symbol for micro, with the exponent that they tell me a micro is on the back of my data sheet. Literally, it's just change the symbol to a number, 10 to the minus 6. Now, QB is 1 times 10 to the negative 6, 1 microcoulomb. And remember, we're dropping the sign of the charge for everything here. R is 1 centimeter. Make sure you make that in meters. What do we end up getting for FAB there? My fab force. Jesse, you got that? 179.8 newtons. Seems reasonable there. That's a pretty big force as well. Not nearly as big as in question number 1. Still pretty big force though. Why is it a lot smaller? My distances are still pretty small, right? We're dealing with microcoulombs, which is a much more normal set of units for charge, right? Okay, let's find FCB. Oh, it is going to be the same, isn't it? Yeah, it's the exact same number. So it's going to be 179.8 newtons as well. So we redraw that. We get FAB, 179.8. We get FCB, 179.8. And then we got that resultant force down here. Do the Pythagorean theorem, and I think it works out to be 254. And theta is going to work out to be 45 degrees there. All right, I got a few questions for you to do on page 538. You're not going to have a chance to work on these right now, but you may have a chance toward the end of class. Depends on how things go for us. It's going to be page 538. I want you to do questions number, I believe it was number 4. Yes, start at number 4, and I want you to go all the way up through number 10. And as I say, hopefully we'll have a chance to work on this a little bit later on in class. If we don't, then you can finish it up for homework tonight. Now, I want to go one step further with what we've been doing and talk about electric fields. Just like last year when we talked about gravitational force, we stepped it up and started talking about gravitational field. From gravitational force to gravitational field, electric force to electric field. What's a field? Well, we can define a field in a number of ways. One way is a line of influence that surrounds something. Right? That's what a field is. It's an influence. It's an invention. It's a human-made construct to help us to see, to understand, to realize that there's an influence of something, even when there's nothing to feel, to experience that influence. There's a gravitational field that surrounds the Earth. Even if there's nothing experiencing that field, the gravity is still there. So we talk about this concept of gravitational fields to describe that, this influence that surrounds the Earth. Another way to define a field, okay, would be an area or a region, let's say. It's the same thing, but just a little bit of a fancier way of saying it. A region in which we'll say an electric force, because we're talking about an electric field here, although this can be, you can substitute what's in brackets here for a gravitational force, or whatever the case may be, depending upon what kind of field you're talking about. A region in which a force would be experienced by an object. Let's say could be experienced, because it depends on whether the object is there, right? It's not going to experience the force if the object isn't there. So a region in which an electric force could be experienced by a charged object. Okay, it's influence that surrounds something. What does an influence do? Well, it causes a force, perhaps on an object that's charged if that object happens to be in that field. Gravitational fields surround objects with mass. Electric fields surround objects with charge. They're both vector fields because they both have a direction associated with them, not in the way they travel, but rather in the way they influence. Gravitational field always causes a mass to accelerate toward the producer. So the Earth pulls an object down towards it. It doesn't just influence the object, it influences it downward. And the electric field's similar. It doesn't just influence another charge, it influences another charge in a very particular direction. As opposed to scalar fields, like a light field, like a heat field, they can influence things, but they don't influence things in a particular direction. There's lights on the ceiling right now. They influence all of us, but they don't influence us in a direction. Light travels in a certain direction from the light bulb to your eyes, but it's not influencing you to go towards the light or away from the light. So we'd say those would be scalar fields. Even though the velocities would be vectors, the field, the influence, would be scalar fields. So how does this all relate to the forces thing? Forces is what we've been talking about for the last few days, whether we're talking about between two charges or three charges along a line or three charges in two dimensions with a 90-degree angle. Field is the influence of something. Force is when something experiences that influence. In other words, in order to have a field, all you got to have is something to cause it. But if we talk about gravity for a second, and we will talk about gravity again, because we can see that and feel that every day ourselves. There's a gravitational field surrounding the Earth. All we need to have the Earth's gravity is the Earth. Right now, Jack is sitting in his desk at a specific spot on the Earth. He experiences that gravitational field. And therefore, because of that, because there's a field at that point and something to experience it, there's a force. But if Jack wasn't there, there wouldn't be a force anymore, but there'd still be a field. Right? The Earth hasn't gone anywhere. The Earth causes gravity. The field is 9.81 there, regardless of whether Jack's there or not. But if Jack's there, there's the field and there's the force. What's a force again? The 5-word definition. A push or a pull. A push or a pull. In order to have a force, in order to have a push or a pull, Jack needs to be there to be pushed or pulled. If Jack's gone, there's still a field, gravity's still there, but there's nothing to push or pull, so you can't have a force. And it's the same thing with electricity. Just a little bit harder for us to visualize with electricity than it is gravity. If you have a charge to cause an influence, there's a field. If you have another charge to feel that influence, then there's also a force. Now, we're going to define the direction of the electric field. Just the same as really we can define the direction of a gravity field. We'll keep going back to that because we can see and visualize gravity fields, and we've dealt with them in Physics 20, so we know about them a little bit already. Don't write down what I'm about to write down with my pen, okay? The gravitational field, we can define it in a couple of ways. One is the way that an object moves when placed in the field. So for instance, if I take my pen and I hold it out here and I let it go, which way is it going to go in the field? Which is it going to move in the field? Downwards, right? So that's the direction of the field, the way that an object moves when placed in the field, downward toward the producer. The other way we can define it as toward the producer. Which way does the gravitational field point? Well, downward, because that's the way that the pen would fall if I let it go. Which way does the gravitational field point? Downward, because the producer is downward. Producer is below me. Now, we define electric field direction not as the way that an object with mass would move if placed in the field, but rather the way that a positive particle would move if placed in the field. Yes? Notice we have to be a little bit more specific with the electric fields. With gravity, there's one kind of mass. Mass is mass. With electricity, there's two kinds of charge, positive and negative. So it was good enough with gravity to say that it's the way that an object with mass moves. But with electric fields, we have to say the way that not just a particle with charge, but specifically a positive particle would move if placed in the field. Here's a producer. Let's say it's a positive producer. Here's the field lines that go out away from that positive producer. If I was to put a positive charge right there, that positive charge would be repelled by the positive producer. So it would move outwards away. Therefore, we define the field arbitrarily as outwards away from this positive producer. It's the way that a positive particle would move if we place it in the field. Now, let's say we took this away. It's gone. Does that change the field? No. The field is outwards, away from the positive producer, because if we put a positive in there, if we put this there, it would move outwards. It doesn't have to be there, but if it was there, it moves outwards, therefore the field is going to be outwards. By the way, if I put a negative in there, which way would it move? Towards it. So positives experience a force with the field, and negatives will always experience a force against the field. Now, we can also define the field as away from the positive and toward the negative. So you can see here, my field, regardless of whether I draw those little charges in there or not, my field points away from that positive producer Or if I drew a negative producer, it would point towards it. Away from the positive, toward the negative. Let's put a little positive in here. Where does it go? Experiences a force this way, toward the negative. A negative would experience a force this way, away from the negative, opposite to the field. All right, let me draw you 3 pictures here. First one, actually 4 pictures. First one, here's a positive charge. Second one, here's a negative charge. Which way does the field point caused by these 2 charges? Well, it points away from positive, and it points toward negative. So there you go. There's the electric field surrounding 2 charges, positive and negative. What if, though, what if I put those 2 charges close enough together that they interact with each other? The field, yeah, they will be attracted towards each other. The field caused by this one is going to look something like this, away from the positive. The field caused by this one is going to look something like this, toward the negative, right? Watch what happens in between, though. Field lines kind of join up there. And it looks something like this. What would happen if I put 2 positives beside each other, close enough to interact? Well, these field lines no longer join up. They don't do this. Rather, they repel each other. It would look something like this. Field lines never join up. When the field lines join like this, we get a force of attraction between the 2 charges. Positive and negative attract. When the field lines don't join, we get repulsion. We're going to talk about a little bit more about electric fields over the next little while. And in our next unit, we'll talk about magnetic fields. Remember that when field lines join up, no matter what kind of field it is, there's attraction. When field lines don't join up, regardless of what the picture looks like, if they don't join up, then we get a force of repulsion. All right?